This is our 8th video on ring theory, and in the last video we looked at the notion of an ideal of a ring as well as its quotient ring, its associated quotient ring. And we want to continue to look at examples of ideals and quotient rings, as well as a simpler way to describe some very common ideals. Okay, so let's recall the definition of an ideal and its associated quotient ring, and then just get going. So a subring I of R is called an ideal if for all A in R and I in I, we have I times A and A times I are in I. So in other words, ideals have this absorption property. You take an element from the ideal and an element from the ring as a whole, you multiply them and you get inside of the ideal. The maybe intuitive way to think about this is like if you take an even number and any integer, well, if you multiply them, you immediately become even. And so the set of all even integers is an ideal, as we saw before. Or if you take a number that's a multiple of 3 and you multiply it to anything, you get another multiple of 3. So again, that's kind of absorption into evenness or absorption into being a multiple of 3. Okay, and so now what about this associated quotient ring? Well, let's say you've got a ring and an ideal, then the quotient ring is, as a set, it's the set of all cosets. We talked about what cosets were last time. And then the operations go like this. So we've got A plus I plus B plus I is equal to A plus B plus I. And again, last time we talked about how these different pluses are kind of playing different roles. I urge you to look back over that if this line still looks confusing. And then down here we've got multiplication defined as A plus I times B plus I is AB plus I. So the product of these two cosets is the associated coset of the product of the two representatives, if you will. And, well, this definition of an ideal up here was necessitated by wanting this quotient ring to actually be a ring. Okay, so I'm going to start by proving something fairly simple, but you will use it from time to time, so it will be nice to have in the books, and that is the ideal test. So we had a subring test before, you might remember that. Well, this is just a version of that for ideals. Let's recall that every ideal is a subring, so we might want to think about checking that it's a subring first, but in fact you can kind of skip a step if you use this test. Okay, so anyway, let's look at this. We've got I, a subset of R, is an ideal if and only if for all I and J and I, and A and R, we have I minus J, A times I, and I times A are all elements of I. So notice here we're combining two elements of I with subtraction and we're getting inside of I. But here we're using this fact that we need this absorption property over here. I guess it's up here. Okay, so I'd like to point out that this forward direction is just clear by definition. If you've got an ideal, then these things are definitely satisfied just by the fact that it's a subring with this absorption property. So that means we need to look at this reverse direction. Okay, so let's get going with the reverse direction. But before we do, I just realized that I left off sort of a hypothesis here that we really need, although we hardly ever use, and that is this fact that I is non-empty. We never use it because if I is empty, you can't really get off the ground. So in fact, we're either always using it and never thinking about it. Maybe that's the better way of talking about this. Okay, so now let's look at this reverse direction. So let's observe up here, we need to first check that this is a subring. So if you might recall, in order to be a subring, you have to have the 0 element, you have to be closed under addition, and you have to have all additive inverses. So let's just make sure we have the 0 element. Okay, so let's say for I in I, we have I minus I is an element of I, but I minus I is equal to 0. We know that I minus I is an element of I because we know for all I and J in I minus J is in I. So we're just using this hypothesis where I and J are the same. Okay, so that means we've got 0 inside of our ideal. So now let's talk about additive inverses. So I'll just put here minus I for additive inverses. Now let's note that for I in I, we have the following, and that is 0 minus I is an element of I. That's because we know that 0 is an I, so we're just applying our condition right here, our I minus j in I condition, to 0 and I. But notice that 0 minus I is equal to negative I. So that does it for that. We've got additive inverses. Okay, now what about a sum? So I'll just put I plus j here to show that the sum is here. And here we've got for I and j is in I, we have I minus negative j is in I, but that's just simply I plus j. We know that minus j is in I from the thing that's right above. Okay, so we've got the additive part of being a subring. Now let's check the multiplicative part of being a subring. So that would be I times j. So now let's notice that for all I times j is in I, notice that j is an element of R. So every element of I is already an element of R. But let's notice that that means that I times j is an element of I. Okay, nice. Well, there we've got it. We've got a subring. Now we just have to check that we have the absorption property. So in other words, we've got a subring with the absorption property. But I'd like to point out that the absorption property is immediate just by what we're given right here. So we've got a subring with this property. In other words, we have an ideal. Okay, so now I'd like to look at the notion of an ideal generated by certain elements. For the rest of the video, unless explicitly mentioned, we're going to take R to be a commutative ring. And well, the main reason for that is that most of these things get to be a little bit complicated or sticky if we are not working with a commutative ring, but you can see some nice things happening if we just restrict to commutative rings. Okay, so anyway, let's say that we're given A1 up to AN in R, then we want to define the ideal generated by these elements A1 to up to AN. And the notation is going to be like this. We'll have these angled brackets with A1 up to AN inside of the angled brackets. And that's going to be defined as everything of the form R1A1 plus R2A2 all the way up to RNAN, where Ri is an element of the ring R. So you can think about this as like taking linear combinations, if you will, of our elements A1 up to AN. Now, if we have a single generator, then we call this a principal ideal. So in other words, if n is equal to 1, we've got something called a principal ideal. And in that case, we would just have brackets with an A, and that would be A times R. So it's going to be all multiples of A, all R multiples of A. Now, you can think about or look into how these things would be defined if you had a non-commutative ring, but like I said, we're not going to go over that. Okay, so now I'd like to prove that in fact, this structure does give us an ideal. Okay, so let's get to it. So let's suppose we have I and J inside of A1 up to AN, and we have R inside of R. So what we're going to do here is use the ideal test that we just proved. Okay, but what does that tell us? Well, that tells us that there exists elements R1 up to Rn and S1 up to Sn such that we can write I as R1A1 added all the way up to RNAN, and we can write J as S1A1 added all the way up to SNAN. So that's just what it means for I and J to be inside of this, well, what will be an ideal generated by A1 up to AN. So now let's look at the difference, and let's check out, we've got I minus J is going to be equal to R1 minus S1 times A1 added all the way up to Rn minus Sn times An. And of course, what I did right there is I used the distributive rule to pull things out. I pulled the A1 out of the right-hand side in all of those terms, and I used associativity and commutativity of addition as well. But I don't think there's a ton going on there, that's that confusing. Okay, but now notice that this is a combination of our A1 up to AN, meaning it's inside of this thing generated by A1 up to AN. Okay, so that means this thing is closed under subtraction. Now let's make sure it's closed under the absorption property. So let's look at R times I, but now observe that that's simply going to be R times R1 times A1, all the way up to R times Rn times A1. Look, that's just multiplying this I here by R, and of course we can use the associativity of multiplication along with the distributive rule to get it into this form pretty quickly. But now, again, this is in exactly the form that we need it to be like inside of this thing generated by A1 up to AN. So this is in this thing generated by A1 up to AN. But these are the two things that have to hold if we're in a commutative ring and we want to show that it's an ideal. If we were in a non-commutative ring, we'd also have to check this I times R was an element of that thing over there. And that's actually where our definition up here would have fallen apart a little bit with this generation within a non-commutative ring. We would have needed a little bit beefier of a definition. Okay, nice. Okay, so now I want to look at some examples. So for our first example, we'd like to look at the ideal generated by 6 and 15 as an ideal of Z. So let's first maybe write that out using our definition over here. So we've got this ideal generated by 6 and 15 is going to be equal to 6x plus 15y, or everything of the form 6x plus 15y, as x and y run over all integers. That's just applying this definition over here. But now I'd like to note the following, and that is if we set, for instance, x to be equal to -2 and y to be equal to 1, then we get the following equation. We get 3 is equal to 6 times -2 plus 15 times 1, which is an element of 6, 15. Okay, but now notice that that immediately gives us the following inclusion. The ideal generated by 3 is contained within the ideal generated by 6 and 15. I think that this equation here is kind of enough to see that, but if you want to see it in slightly more details, let's observe that if we take 3 times n inside of the ideal generated by 3, notice by our rule down here, everything inside of the ideal generated by 3 is of the form 3 times an integer. And then let's notice that we have 3 times n can be written as 6 times minus 2n plus 15 times n, which is an element of 6, 15. Okay, well, essentially what we did is we just took this equation right here and multiplied it by n. So starting with an element of the ideal generated by 3 and showing that it's inside of the ideal generated by 6 and 15 is exactly what it takes to prove this subset relationship right here. I guess sub-ideal relationship. Now let's also notice that we have containment the other way. So we have the ideal generated by 6 and 15 is a sub-ideal of the ideal generated by 3. And this is actually like a little bit easier to check. So notice that if we take an arbitrary element of the ideal generated by 6 and 15, so 6x plus 15y is inside of that. Well, we can write that as follows. 3 times 2x plus 5y, and that is pretty clearly inside of the ideal generated by 3. But of course, if you've got this set inclusion going both directions, then that means that these two are in fact the same. So we get this ideal generated by 6 and 15 is in fact equal to the ideal generated by 3. So look at what we tried to do here. We tried to find an ideal of Z, which was not a principal ideal. You know, we thought it might be generated by 2 elements. But then via a pretty straightforward calculation, we proved that it was actually generated by one element. Okay, and then we're going to look at a more general version of this phenomenon in just a little bit, but that motivates us to think that perhaps every ideal of Z is one of these principal ideals. Okay, so now let's look at this next example. Let's take the ideal generated by x and 3 inside of Z adjoint x. That's polynomials with integer coefficients. Well, we can use our definition up here to say that this is simply equal to x times p of x plus 3 times q of x, as p of x and q of x run over all integer coefficient polynomials. Okay, but now I claim that this is equal to the set a(n) x to the n plus all the way down to a1x plus 3a0, and that's where ai are all integers. In other words, it's all polynomials with integer coefficients where the constant term is a multiple of 3. Now, if you saw this ideal in this form over here way on the right, you might think that you'd have to check that it's an ideal. But seeing it over here as the ideal generated by x and 3, and keeping in mind that we just proved that something like this is always an ideal, that means that we know automatically that the thing over there is also an ideal. Okay. Now, you might say, well, is this a principal ideal? Can I rewrite this as being generated by a single polynomial? And in fact, we can't, and we're going to do that a little bit later in the video. But what I'd like to do right now is look at the associated quotient ring. So let's look at Z adjoin x mod, this ideal generated by x and 3. And I claim that this is going to have 3 elements. So it's going to have the coset 0 plus this ideal. It's going to have the coset 1 plus this ideal. And then it's going to have the coset 2 plus this ideal. And I think that this will be pretty clear if we look at the following observation, and that is x plus this ideal is equal to the coset 0 plus this ideal. And that's because x minus 0 is equal to x, which is an element of this ideal. So that means anytime you see an x, that's simply just 0 inside of this quotient ring. So if you've got a polynomial of large degree, well, in fact, you don't have a polynomial of large degree because all of the x's are 0 inside of the quotient. And then similarly, we have 3 plus this ideal, so that's going to be x comma 3 is equal to 0 plus this ideal x comma 3. And that's even easier. That's because 3 minus 0 is an element of this ideal. So we have all of the x's are 0, and then the constant terms are going just like we were to work modulo 3, if you will. So that leaves us with these 3 elements in the end. Okay, so let's look at some other examples. So now let's look at the quotient of the Gaussian integers mod the ideal generated by 1 plus I. So just as a sketch over here, notice that 1 plus I is everything of the form 1 plus I times a plus bi, as a and b run over all integers. And that's because that's how I parameterize the elements of the Gaussian integers, by an integer plus an integer times I. But now I could multiply this out if I wanted to, and let's observe that we're going to get a minus b plus a plus b times I, where a and b are in Z. So that's the shape of this ideal in this like kind of weird relationship between the real parts and the imaginary parts of our elements. But I think we could use this to get an idea of what the quotient ring looks like, but I think it's maybe a little bit harder than it needs to be. I think we can use some clever calculation to get a better idea of what the quotient ring is. So let's observe that 2 minus 0 is simply equal to 2, but that's also equal to 1 plus I times 1 minus I. But notice, since this is a multiple of 1 plus I, and 1 plus I is in our ideal, that means that this is in the ideal generated by 1 plus I. But now look at what we've got. We've got 2 minus 0 is an element of the ideal. But then that means inside of the quotient ring, so I'll say in our quotient ring, Z adjoin I, or the Gaussian integers, mod this ideal generated by 1 plus I, we have 2 plus the ideal, so that coset, is equal to 0 plus the ideal. So the coset for 2 is the same thing as the coset for 0. But we get a lot out of this. Notice the coset for 2 being the same thing as the coset for 0 means the coset for 1 is the same thing as the coset for negative 1. I essentially just like subtracted 1 from both sides of that equation up there. Really, I subtracted the coset attached to 1 from both sides of that equation. Okay, nice. But now let's also note that the coset 1 plus I, or associated to 1 plus I, is definitely equal to the coset associated to 0. And that's because 1 plus I is inside of the ideal. But that means the coset I plus our ideal is the same thing as the coset minus 1 plus our ideal, which is the same thing as the coset 1 plus our ideal. Okay, cool. Now, all of these little calculations that we've done on the board leads us immediately to this coset A plus BI plus our ideal is equal to the coset A plus B plus our ideal, because I plus the ideal is the same thing as 1 plus the ideal. So I just replace this I with 1. But then observe that this is simply going to be 0 plus the ideal generated by 1 plus I if A plus B is even, because if it's even, it's a multiple of 2, but we just showed that 2 was equal to 0 inside of our quotient. And then it's going to be 1 plus our ideal if A plus B is odd. And well, that's because if it's odd, we can take out an even number, leaving us with a remainder of 1, and then the even number is equal to 0. That's by calculations that we've done similarly before. So in the end, what does that tell us? Well, that tells us that we only have 2 elements here. So this Z adjoin I mod, the ideal generated by 1 plus I, simply has the elements 0 plus 1 plus I, and then 1 plus the coset, or sorry, the ideal 1 plus I. Then if you wanted to, you could make an addition and a multiplication table for that, but it's actually fairly simple, so I'm going to skip that and move on to our next example. So for our next example, I'd like to look at the Gaussian integers, Z adjoin I mod, the ideal generated by 2. So let's quickly observe that 2 minus 0 is an element of this ideal, which means 2 plus the ideal is equal to 0 plus the ideal. In other words, the coset associated to 2 is the same thing as the coset associated to 0. But that immediately tells us that 1 and negative 1 are the same inside of this quotient. And then via similar calculations, we can show that this quotient has 4 elements. So we've got the coset attached to 0, the coset attached to 1, the coset attached to I, and the coset attached to 1 plus I. Notice if I add any of these with themselves, I end up with 0. That's because I get a multiple of 2. And then if I do like this coset 1 plus 2I plus this coset I plus 2, I get this coset 1 plus I plus the ideal generated by 2, and then you can do similar calculations as well. Now I'd like to introduce some notation which is going to simplify our lives a little bit. And let's write A bar to be the coset A plus our ideal generated by 2. And now I'd like to make maybe a quick addition and multiplication table of this quotient ring just to get a feel for what's going on. So we'll have 0 bar, 1 bar, I bar, and then 1 plus I bar. So this will be our addition. So 0, 1, I, and then 1 plus I. Okay, so there are our 2 charts to fill in. So let's fill in the addition table first. I think adding 0, there's not really much going on here, so I'm just going to do that quickly. So there we've got our addition by 0. Of course, 0 bar, if you will, is the additive identity, so that doesn't change anything. Now let's add 1. So 1 bar plus 1 bar is going to be 0 bar, and that's Well, because 1 plus the ideal plus 1 plus the ideal is 2 plus the ideal, but 2 is an element of the ideal. So in other words, those cosets add to just the 0 coset. And then this one is pretty straightforward. This is going to be 1 plus I bar because we've got 1 bar plus I bar. And then what about this 1 bar plus 1 plus I bar? Well, that's going to give us I bar. And that's because the 1 plus 1 part, if you will give us 2, but 2 is 0 inside of this quotient. Now we can fill in the same column just because we've got commutativity. Now I plus I will be 2I, but 2I is 0 inside of our quotient, so I might as well put 0 there. I bar plus 1 plus I bar will give us 1 plus 2I bar, but that 2I is 0, so that's going to give us just 1. And then here we have 1 here, and then kind of filling it all out, we get a 0 right there. So observe that everything is its additive inverse, which I think is kind of interesting. Okay, so next up, let's look at a multiplication table. Multiplying by 0 is pretty uninteresting, so I can add that in real quick. Multiplying by 1 is similarly uninteresting, so I can multiply, or I can include that pretty quickly as well. Now let's do multiplication by I. So I times I is -1, but observe that -1 is the same thing as 1 inside of our quotient. So that means that we've got a 1 bar right there. And then, well, let's look at this square and this square kind of on its own. So we'll do I bar times 1 plus I bar. So I'm going to write this out as cosets. So that's going to be I plus 2, and then 1 plus I plus 2. But now if I do that product, I'm going to get I times 1, but I times 1 is going to give us I, and then I times I, but that's going to give us -1, so we're going to get I minus 1, plus our coset generated by 2, but -1 is the same thing as +1, so I get that this is I plus 1 plus the coset generated by 2. So that's pretty interesting. If I multiply I with 1 plus I simply get 1 plus I. So here I get that this is 1 plus I bar, and then this is simply also 1 plus I bar. Now let's do one more calculation. So that would be this 1 plus I times 1 plus I. Let's maybe bring that over here, and maybe I won't write out the cosets in this case. Let's just do 1 plus I times 1 plus I. So if you multiply that out, you'll pretty easily see that this is equal to 2 times I when everything is said and done with the distributive rule. But 2 times I is 0 inside of our quotient, so this is in fact 0 bar. So we've got something that squares to 0 inside of this quotient ring. Okay, so let's look at another nice example before we look at some classic results. So now let's look at Z2 adjoin X. So that's going to be polynomials where the coefficients come from Z2, so that's either 0 or 1, and then the operations are modulo 2. Okay, so Z2 adjoin X mod the ideal generated by this polynomial x squared plus x plus 1. So that's just all polynomial multiples of this polynomial. Now, before we really get started, I'd like to observe that inside of Z2 adjoin X, the polynomial x squared minus x minus 1 is the same thing as the polynomial x squared plus x plus 1. And, well, that's because -1 and +1 are the same thing inside of Z2. I think that kind of goes without saying. Okay, so now I'd like to observe the following, and that is that x squared minus x minus 1 plus our ideal is equal to 0 plus our ideal. I think that's obvious because this polynomial is the same thing as the polynomial that's generating the ideal from our observation up there. But that means that those cosets are the same. But now I can add x and 1 to both sides of this equation, and I see that x squared plus the ideal generated by our polynomial is the same thing as x plus 1 plus the ideal generated by our polynomial. So what that means is that anytime we see a polynomial of degree larger than or equal to 2, we can simplify it to a linear polynomial with this relationship right here. So let's observe how that might go. So let's say we're looking at the coset attached to the polynomial x to the fourth plus x plus 1. So I've got that plus our ideal. So like I said, we're looking at the coset. But now what I'd like to do is take this x to the fourth and rewrite it as x squared squared, and take this x cubed and write it as x times x squared. And of course, I'm not going to rewrite the 1 as anything, so I just have that. But now I can use my relationship up here that I know that x squared is x plus 1 inside of the quotient to rewrite this as x plus 1 squared plus x times x plus 1. I just replaced all of those x squareds with x plus 1 by our observation up there. Then, of course, we're inside of this quotient ring, so I need plus the ideal because this is really just a coset. But now if I square this x plus 1, I'm going to get x squared plus 2x plus 1, but 2x is 0 inside of z2, so that's just x squared plus 1. And then if I multiply this out, I'm going to get another x squared plus 1, and then I've got this plus 1 hanging on until the end. Great. But now I'd like to observe that this x squared and this x squared will add together to give us 0 because it gives us 2x squared. And then this 1 and this 1 add together to give us 2, which is 0. So let's observe that in the end, this is essentially just the coset 1 plus our ideal. So again, what did we just show? This coset associated to our polynomial x to the fourth plus x cubed plus 1 was simply the coset attached to 1. Okay, so now I'd like to maybe use a simplifying tactic similar to the one that we did before that will allow us to write down a multiplication and addition table for this quotient ring. So let's recall two things that were important about this quotient ring. First of all, the coefficients occur in Z2. So that means the only possible coefficients are 0 and 1. And that's because, well, again, they're in Z2. And the other thing that was important was that x squared plus the ideal, so that coset, was the same thing as the coset x plus 1 plus the ideal. And that's via a calculation that we did before. So now I'd like to introduce some notation, and that is I'm going to call alpha the coset x plus our ideal. But observe that this equation right above turns into the equation alpha squared is equal to alpha plus 1 using this notation. So I think this is a nice simplifying notation. Now let's observe that our quotient is really made up of 4 cosets. The coset attached to 0, the coset attached to 1. Those are the only constant cosets, and by constant I mean there are no x's in them. And that's because our only coefficients, and thus our only constant terms, are 0 and 1. And then we've got x, well, x plus 0, so the coset attached to x plus 0, and then the coset attached to x plus 1. And again, we don't need anything squared or higher because we've got this simplification tool, which we explored on the last board. And then we only need 0 and 1 as coefficients. So that gives us all linear polynomials over here. So again, we've got 4 different elements. But using my notation, I can write that as 0, 1, alpha, and alpha plus 1. So now I'll maybe leave it to you to make an addition table. There's not really much going on here. You just add these, keeping in mind that when you get a coefficient of 2, that becomes 0. So let's make a multiplication table. And perhaps I'm not going to include 0 in my multiplication table because 0 times anything is just 0. So there's not really anything going on there. So that means I've got 1 alpha and then alpha plus 1 inside of my multiplication table. Now, multiplying by 1 is like straightforward. I just get what I started with. That is the multiplicative identity inside of our quotient. Now let's do alpha times alpha. But alpha times alpha is alpha squared, so that gives us alpha plus 1. Then let's do alpha times alpha plus 1. Maybe we'll do that over here. So alpha times alpha plus 1 is going to be alpha squared plus alpha. But then we know alpha squared is alpha plus 1, so that's alpha plus 1 plus alpha. But that's 2 alpha plus 1, but that's just 1 because 2 is equal to 0 in this world. So that means we have alpha times alpha plus 1 is 1. And likewise, if you do alpha plus 1 times alpha, you also get 1. So that tells me that alpha and alpha plus 1 are multiplicative inverses. So that's pretty cool. Now let's fill in this last portion of our multiplication table, the alpha plus 1 times itself. So we've got alpha plus 1 squared, but that's going to give us alpha squared plus 1. Notice there's no cross term because the cross term would be 2 alpha, which is 0. But then we know alpha squared is alpha plus 1, so that's going to give us alpha plus 1 plus 1. But if you do that, we're just going to get alpha because 1 plus 1 is 2, which is 0. So that means, what do we have here? We've got alpha plus 1 times alpha plus 1 is alpha. But I'd like to observe here that every non-zero element is exhibited inside of this multiplication table. And furthermore, every non-zero element here has a multiplicative inverse. 1 is its own multiplicative inverse. And then alpha and alpha plus 1 are multiplicative inverse pairs, if you will. So what does that tell us? Well, we've got a commutative ring with 1 where every element that is non-zero has a multiplicative inverse. In other words, this quotient right here is a field. Now later, we'll be able to tell how to get more fields like this. And by that, I mean where we've got quotients, where we've got polynomial rings over a field, mod, certain ideals generated by polynomials. Okay, so now, like I said, we're gonna prove some more general classic results. Okay, so let's prove this simple result that's got kind of a homework problem feel to it. Let's say that we're inside of an integral domain. Now we're gonna show that the principal ideal generated by an element A is equal to the principal ideal generated by the element B if and only if A and B are associates. Let's recall that they're associates when they differ by a unit, if you will. In other words, A is equal to B times some unit. And remember that a unit is a number or an element that has a multiplicative inverse. Okay, so anyway, let's get going with this forward direction. So let's observe that A is an element of the ideal generated by B, and we know that B is an element of the ideal generated by A. Well, and that's because, well, A is in the ideal generated by itself. That actually subtly requires that R contain the identity element, but integral domains contain the multiplicative identity, so we're okay there. And then B is in the ideal generated by itself, so that means B is also in this A over here. Okay, nice. But that tells us that there exist these ring elements R1 and R2 inside of the ring, such that A is equal to R1 times B, and B is equal to R2 times A. Okay, nice. But now what I'd like to do is take one of these, perhaps this B is equal to R2 times A, and multiply it by R1. That means that R1 times B can be written two different ways. It can be written as R1 times R2 times A using the yellow underline. So maybe I'll just use this yellow underline right here to show that I'm coming from the yellow underline up there. And then the blue underline right here will push us off to the left to write this as A. But now observe we've got A is equal to R1 times R2 times A. But I'm going to take this A over here on the left and write it as 1 times A, and then use the fact that inside of an integral domain, I have cancellation. So that tells me that R1 times R2 is equal to 1, but that means that R1 and R2 are units. But if R1 and R2 are units, that means that A and B are associates by the definition of being associates. So that finishes this forward direction. Now let's look at the reverse direction. Okay, so we know that A and B are associates. So let's find units, U1 and U2, inside of our ring with A equals B times U1. And then we've got B is equal to A times U2. But now let's prove these ideals are the same using double set inclusion. So let's take an X inside of my ideal generated by A, but that means that X is equal to R times A for some R inside of R. But now I can write R times A as R times B times U1. So here we've got R times B times U1 because A is equal to B times U1. But in turn, that's going to be the same thing as R times U1 times B, which is an element of the ideal generated by B. So let's see, starting here and ending here is exactly what we need to show the ideal generated by A is a sub-ideal of the ideal generated by B. Now let's go in the reverse direction. So let's take perhaps something we would call y inside of the ideal generated by B, but that means that y is equal to s times b for some s inside of my ring R. But now I can rewrite that as s times a times u2 using my equation up there. But then I can rewrite that as s times u2 times a, which is an element of the ideal generated by A. But now the same argument that we just used, where A and B are replaced, will now show us that the ideal generated by B is a sub-ideal of the ideal generated by A. But of course, if we've got those two subset relationships, that means that these are the same. Okay, so let's move on. Okay, so now I've got two related results that we're going to do back to back. The first one is that every ideal of the integers is a principal ideal. And then we're also going to prove that every ideal of a polynomial ring over a field is also a principal ideal. And so that keeps building together these parallels between integers and polynomials over fields that we mentioned before. Okay, so let's look at this first one. So every ideal of Z is principal. So let's say we've got an ideal of Z, and that's going to break into two cases. One case is very simple, and that ideal is just the zero ideal. So the element, the singleton zero is an ideal. It's just maybe what we would call the trivial ideal. But that being said, it is the ideal generated by zero, so it is principal. Okay, so now let's look at case two, which is I is not the zero ideal. But that means that there exists an element of Z, which we'll call M, that's non-zero, such that M is an element of I. Okay, but now note that M or minus M is an element of the natural numbers. That's because if M is a non-zero integer, then it's either positive or its negative is positive. Either way, we get some sort of positive integer here. But notice that M is an element of I, and pretty clearly negative M is also an element of I, because I is a subring. But that tells us that our ideal I intersected with the natural numbers is non-empty. So that means it's a non-empty subset of the natural numbers. Well, every non-empty subset of the natural numbers has a minimal element. So let's take that minimal element. So let's take n to be equal to the minimal element of I intersected with the natural numbers. And then this claim is going to finish it all off. And the claim in question is that the ideal that we've been working with is simply the principal ideal generated by n. Okay, so let's see how this goes. We've got to do double set inclusion like we do to show any two sets are equal. So let's suppose first that we've got an element x in the ideal generated by n. But that means that x is equal to n times k for some integer k. But now let's point out that this k is an integer. This n is an element of the ideal because it's in the ideal and it's a natural number. But then by the absorption property, we know that that means that x is inside of the ideal because we're multiplying an element of the ideal with an element of the ring as a whole. But let's see, starting here at x is in the ideal generated by n, ending here with x is in our ideal, means the ideal generated by n is a sub-ideal of I. Okay, so that gives us one of the directions we need. Okay, so next, let's suppose that A is an element of I, and let's use the division algorithm to write A as n times q plus r, where r is between 0 and n, including 0 but not including n. Okay, now that's going to break into two cases. So one of the cases is going to work, it's okay if you will, and the other case will give us a contradiction. Okay, so the first case is that r, our remainder over there, is equal to 0. Notice that's an allowable value of our remainder. But in that case, we get a is equal to n times q, but n times q is an element of the ideal generated by n, but that tells us that a is an element of the ideal generated by n. But to finish this off, that means that I is a sub-ideal of the ideal generated by n. But now if you put together these two magenta boxes, you'll have what we need. You'll have the claim proved. But now let's look at this other case, and that would be r is not equal to 0. But that means we have the following. We've got, let's see, r can be written as a minus n times q. But now if r is not equal to 0, then that means it's a natural number, okay. And then also writing it as a minus n times q puts it inside of our ideal I. That's because a is in I, and then n times q is also in I guess like from the first part of our proof. So that means this is an element of I intersect n. But that's a contradiction. That contradicted the minimality of n, because notice what we have is we've got an element of I intersect n, which is smaller than the smallest element in that set. But of course, that's impossible. But then we have it. We ended up proving that our ideal is a principal ideal. Okay, so now let's prove the same result for polynomials over a field. All right, so now let's suppose we've got an ideal of f adjoint x. That's the ring of polynomials over a field f. That's an arbitrary field. But we're left with the same two starting cases. I is either the trivial ideal, in which case it's immediately principal, or it's not the trivial ideal. So if it's not the trivial ideal, that means that it contains a polynomial of degree 0, 1, 2, 3, 4, so on and so forth. And that's important because we've been taking the convention that the 0 polynomial does not have a degree. Sometimes people say it has degree minus infinity, but we've just said that it doesn't have a degree. Okay, so now what I want to do is take p of x inside of I of minimal degree. So what do I mean by minimal degree? Well, that means the degree of p of x is the smallest possible degree of all polynomials inside of I. So perhaps that's 0, perhaps you get a constant polynomial. So perhaps that's a polynomial of degree 2. It doesn't really matter what the degree is, it matters that it's the smallest possible degree. Okay, now we're going to finish this off with a claim which is very similar to the claim that we just saw before, and that is that the ideal I is, in fact, the principal ideal generated by p of x. Okay, so let's prove that. So let's maybe clearly via an argument just completely in parallel to what we did in our first proof, we have that the ideal generated by p of x is a sub-ideal of I. That follows immediately because p of x is an element of I, as we saw before. Okay. So now let's prove the containment the other way. So let's take f of x inside of I. And then let's use the division algorithm with p of x. So what does that mean? Well, that means we've got f of x is equal to p of x times q of x plus r of x with r of x equals 0, or the degree of r of x is less than the degree of p of x. So that was the rule for the division algorithm within a polynomial ring. Now that's going to boost up to two different cases just like we had before. So if we've got r of x is the 0 polynomial, then that means that f of x is equal to p of x times q of x, but that's inside of the ideal generated by P of x by definition. But that means that our ideal I is a subset of the ideal generated by P of x. But now what's the other case? The other case would be R of x is not 0. And I guess we can't really say that subset relationship until we really finish this thing off. But I guess we jumped the gun there, but that's okay. So let's say R of x is not 0. But then what do we have? We have R of x is equal to f of x minus p of x times q of x is inside of the ideal I with lower than minimal degree, right? Because if this is not the 0 polynomial, then its degree has to be lower than the degree of p of x. But the degree of p of x was a minimal possible degree, so we found something with a smaller than minimal degree, but of course that is a contradiction. Meaning that this first case, where our remainder was 0, is really the only case, meaning that we did have a principal ideal. Okay, so now that we've shown these two nice rings only have principal ideals, let's give a definition to rings that only have principal ideals, and then finish it off with a couple of examples. Okay, so here's our definition that we were flirting with during our last result. So we say an integral domain is a principal ideal domain if every ideal is a principal ideal. And we often shorten a principal ideal domain to PID. So here are some examples. So we just showed that Z was a principal ideal domain. Every ideal was principal. We also showed that polynomials where the coefficients come from a field was also a principal ideal domain. So that means like Q adjoin X, Z3 adjoin X, so on and so forth. Now, in fact, the Gaussian integers Z adjoin I are also a principal ideal domain, but we haven't given evidence that that is the case. But I will tell you that those are a PID as well. Now here's some non-examples. If you take polynomials with integer coefficients, that's not a PID. Or if you take this quadratic extension of the integers, which we've looked at in a couple of other videos, Z adjoin the square root of -5, that's also not a PID. And I'd like to prove that those are not PIDs, starting with Z adjoin X. We'll show that the ideal generated by X and 3 is not a principal ideal. So let's first observe that 1 is not an element of the ideal generated by X and 3. So that means that the ideal generated by X and 3 is not equal to the entire ring. Okay, so I don't think that really requires much proof. I think it's pretty clear, especially because we looked at this ideal earlier and we saw that all of the constant terms inside of the polynomials inside of this ideal were multiples of 3. 1 is obviously not a multiple of 3. Okay, so now let's, by way of contradiction, suppose that X3, in other words, the ideal generated by those two elements, is principal. And let's say that it's generated by P of X. So notice that 3 is an element of this ideal, but that means that there exists a polynomial f of x with 3 is equal to P of X times f of X. Because, like I said, we're assuming this is a principal ideal generated by P. And then we also know that X is an element of the ideal generated by X and 3. So since we're assuming that it's principal, that gives us a polynomial G of X with X is equal to P of X times G of X. But now let's observe the following. This thing that I'm putting a pink box around, 3 is equal to P of X times f of X, tells us the following information. The degree of P of X is equal to the degree of f of X, which is 0. And that's because the degrees add when you take the product, and the degree of the number 3 is 0. But then 3 is a prime, so that tells us that P of X is either 1 or P of X is the polynomial 3, just the constant 3. Now, we know that it is not 1 because of our statement up here that 1 is not an element of the ideal. So that means that this polynomial really has to be the constant polynomial 3. Okay, so now let's loop that back into this over here and see what that gives us. So that gives us x is equal to 3 times g of x. And now observe that g of x must have degree 1 just based off of this equation right here. So that means that this is 3 times ax plus b. In other words, it's 3ax plus 3b. But observe that tells us that b is equal to 0. And it tells us that 3 times a is equal to 1 with a an integer. Of course, that's impossible because 1 is not a multiple of 3. Okay, good. So we just proved that Z adjoint X is not a principal ideal domain. Now let's finish everything off by showing that Z adjoint the square root of minus 5 is also not a PID. So we'll show that Z adjoint the square root of minus 5 is not a PID by showing that the ideal generated by 3 and 1 plus root minus 5 is not a principal ideal. So how can we do that? Well, first, we'll show that 1 is not an element of this ideal, which tells us that this ideal is not everything. So let's suppose, or I guess I should say by way of contradiction, let's suppose that 1 is an element of this ideal, but that tells us that there exists a plus b root minus 5 and c plus d root minus 5 with 1 is equal to 3 times a plus b root minus 5 plus 1 plus root minus 5 times c plus d root minus 5. Remember, it's just a combination of those two generators. But now we can do just some arithmetic here, taking apart the real and imaginary parts, and we'll see that this is equal to 3a plus c minus 5d as the maybe real part. And then we've got 3b plus c plus d times the square root of minus 5. That's the imaginary part. But now, just by looking at the real and imaginary parts of both sides, we see that this pink underline has to be equal to 1 because that's the real part of this other side. And this orange underline has to be 0 because that's the imaginary part of this other side. So that gives us a system of equations. Notice we have 3a plus c minus 5d is equal to 1. And we also have 3b plus c plus d is equal to 0. Now what we'll do is take the difference of those two equations. That's going to cancel the c out and leave us with 3 times a minus b. And then minus 6 times d is equal to 1, because we just got 1 minus 0 over there on the right-hand side. But now let's observe that this left-hand side is a multiple of 3. It can be written as 3 times a minus b minus 2d equals 1. But that gives us the same kind of contradiction that we had previously. We have 3 has a multiplicative inverse inside of the integers, which is kind of obviously not true. Or equivalently, we have 3 divides the number 1, which is also not true. So that gives us our contradiction showing that 1, and I'll just put this as a note up here, that 1 is not an element of the ideal generated by 3 and 1 plus the square root of minus 5. Which means that this ideal is not the whole ring. So we're dealing with a proper ideal here. Okay, so now let's prove that it's not a principal ideal. Okay, so moving on to proving that this is not a principal ideal, we'll do this towards a contradiction as well. So by way of contradiction, let's suppose that our ideal 3, 1 plus the square root of minus 5 is equal to the ideal generated by a plus b times the square root of minus 5. Okay, but that tells us that 3 is a multiple of this a plus b root minus 5 because 3 is in the left-hand side, so it has to be 3 inside of the right-hand side as well. So we can write this as a plus b times the square root of minus 5 times some number that I'll just call alpha. We don't actually need the real and imaginary parts of that. And then we also know that 1 plus root minus 5 is going to be a multiple of this a plus b root minus 5 for the same reason. It's in the left-hand side, so it's in the right-hand side. And I'll just say that the multiple of that is beta. And that's where alpha and beta are inside of this quadratic extension, z adjoining the square root of minus 5. Now what I'll do is I'll take the norm of both sides of this equation, or both sides of these equations. So it's been a couple of videos since we worked with the norm, but when we were looking at these quadratic extensions maybe a little bit more carefully as we were building up our examples to work with, we used the norm kind of from time to time. So the norm of the left-hand side of this is 9. The norm on the right-hand side of this is going to be a squared plus 5 times b squared times the norm of alpha. Again, because the norm of a product is the product of the norms. And then the norm over here on the left-hand side of this 1 plus root minus 5 is 6. And then here it's going to be a squared plus 5b squared times the norm of beta. But observe that the a squared plus 5b squared divides 9 and it divides 6. So let's write that down. A squared plus 5b squared is a divisor of 9 and 6. But if it's a divisor of 9 and 6, that means it's a divisor of the GCD of 9 and 6. So that means that a squared plus 5b squared must indeed divide the number 3, because that's the GCD of 9 and 6. But let's observe that that immediately tells us that b is 0. And that's because a squared plus 5b squared is strictly bigger than 3 if b is not 0. Because we've got this 5 times b squared term. But then that means that either a squared is equal to 3 or a squared is equal to 1. Because those are the only divisors of 3, because 3 is a prime. Now, if a squared is equal to 3, then we have an immediate contradiction because no integer squares to the number 3. But that means that a squared is equal to 1. In other words, a is equal to 1. But look at what we've got here. We've got a is equal to 1, and we have b is equal to 0. But that means if we go up here, our original ideal is simply the ideal generated by 1. I guess I really should have here plus or minus 1. So the ideal generated by plus or minus 1. But either way you have that, you get that this is equal to the entire ring, which from our first step we know is false. So that means we've reached a contradiction, meaning that this is not a principal ideal. Okay, so now I'm going to leave you with some exercises. All right, I've got 3 exercises for you. The first is to prove that this ideal generated by a1 up to an is the smallest ideal containing these elements. Now, what do I mean by the smallest ideal containing these elements? Well, that means if I have another ideal containing these elements, maybe we'll call it I, then the ideal generated by those elements is a sub-ideal of I. So that's generally what it means to be the smallest that does something in this context. But now let's observe that this gives us some sort of idea for how we should define the ideal generated by a1 up to an in a non-commutative ring. We would define it as the smallest ideal containing those things, and then just see what that meant in our non-commutative ring. All right, so next up, let's say that we're within a commutative ring, which I guess we were up here as well. And let's set I equal to all elements of R, I'll call them A, where there exists a natural number n such that a to the n is 0. And let's show that that is an ideal. And just FYI, this is the set of all nilpotent elements within our ring. So to be nilpotent is to be able to be raised to a power and achieve 0. Okay, So next up, let's show that the following quotients are fields. The first is z adjoin x mod the ideal generated by 3 and x squared plus 1. So it's generated by two things here because this is not a principal ideal domain. Then the next one is z2 adjoin x mod the cubic polynomial x cubed plus x plus 1. And that's a good place to stop.